Okay, so the map is going to be the last of our data structures that we're talk about. We're exiting data structures hell. We have the set, which we talked about. We talked about the sequence. We talked about the stack. We talked about the queue. Am I missing any of them? I think those are the big four. And then today we're going to be adding one more to that list, which is the map. The map is kind of interesting. Well, the map also has a sub data structure known as the pair, but we will get into that. At its most fundamental level, a map is a collection of what are known as key value pairs. So reference locations which point to and from a key and a value. The key and the value can be pretty much anything. So you can have keys which are strings, which lead to values which are integers. You can have keys which are integers, which lead to values that are strings. You can have keys of booleans that lead to values which are simple writers for some reason. The one stipulation or constraint that we have is that all keys are unique. So we'll get into the mathematical model of this, but essentially, what you need to know about maps is that if you have a key and then you have another key and those two keys are the same thing, the value in the map is going to be the exact same. It has to be. Values can be unique, keys cannot. You can think of this like keys. It's a key. Keys are unique in the fact that they only usually open one thing. You can think of values as a treasure chest or like a I'm trying to draw like the Minecraft. That doesn't work out well. What's contained within that chest could be many different things. It could be the same thing. You could have a key that's a string called Stephen that leads to a value which is 5, and then you could have another string called Sammy which leads to another value which is also 5. Values do not have to be unique. Keys do. That's if you take away one thing before you fall asleep today in class. Remember that keys are unique, values are not. And that's it. We can skip the other 65 slides. Just kidding. The map component allows you to manipulate mappings. Right. These are called mappings. So we map a key to a value. From keys of any type K. K in this case is taking on the form of our good friend T, except T got a little tired, so we're using different letters now. K, generic type. V, generic type, can take on anything. So you can have keys which are strings. You can have keys which are ints, doubles. Must always be reference types, as most things have to be. Maps are basically a very simple database of keys and their associated values. So you'll get into databases like SQL, but this is at its fundamental for a key value store, which is a way to store a database of things. So you could imagine if somebody was psychotic, they could build Carmen from the ground up, and they could use a key value store to store everybody's Buck ID number, that little number that's on your Buck ID, where the key would be your first and last name, maybe your middle name too, because people could have the same first and last names. And then the mapping would be the value. Actually, a better idea would be to do a mapping between your Buck ID number, which is unique, and then your actual name, which is a string. So that would be one example. Because, for example, my father's name, Stephen Ignazik, also went to OSU, so that would fail if we did it the other way around. But Buck ID numbers, I believe, are unique, or they should be. Oh, for example, if you need to keep track of the exam grade for each student, you might use a map from a string, their name, to an integer. That might actually not be the best idea because people can have the same name. So maybe you should do an integer to an integer, which is their Buck ID number to their grade. Things to think about when you're building components or when you're building databases. Okay, here is the nightmare fuel diagram that we include in almost every slide deck now. Although you can see that we implement or we inherit, or we implement the iterable class, which map kernel and map extends from. Does anybody want to take a shot? What can we do because we are implementing the iterable interface? Yeah. Yes, we can have a for each loop, which loops over all of the keys and the values, which you will see is actually a very useful thing because if you don't know what the keys are in the map, it's going to be very difficult to loop over them because of a reason you'll see why very soon. Standard has 3 methods: clear, new instance, transfer from. Just get them tattooed on you at this point, honestly. They're very important. Map kernel has contracts for 6 methods: add, remove any, value, has key, size, all of which we will get into. And then map has an additional 5 methods that could be useful to you, such as replace value, key, has value, shares key with, and combine with. Most of the methods in the map interface that we implement are to help deal with the fact that keys have to be unique, especially shares keys with and combine with. Because if you have 2 maps, you can't combine them if they have multiple keys because of the mathematical model of maps, which we'll get into. Iterable has a contract for 1 method, iterator, which allows you to loop over all of the what are known as pairs in a map. I guess that's the other stipulation. Maps technically store what are known as pairs, but pairs are just keys and values. So you want to redraw the diagram so that it is accurate, I suppose. You would say that a map is something like this, where each entry is what's known as a pair, which has a key and a value, which are both reference types. This is a pair, which has a key and a value type. So you can see this is the one. I know I say draw pictures, but really draw pictures because otherwise you will get confused as to how the references play out. Value. And then all of these are reference types, which can be of any type, as long as it's a reference type. Those are squares, by the way. I know they don't look like them, but okay. So the mathematical model is very confusing for a map because maps are very confusing, at least mathematically. It's modeled by a finite set of ordered pairs of type KB with the function property, i.e. that no 2 pairs in the set have the same K value. All keys are unique. This is sometimes called a finite partial function from K to V, because if you have the key, you can get the value because they're unique. If you have a key value pair where the key is a string and then you have a string, there's no ambiguity as to what value you're referring to because there's only unique keys. So you know exactly what value it's pointing towards. And here's that mathematical function. We call the partial function a finite set of key value pairs where key is K, value is V. We have an exemplar here, M, where the constraint being that for every key 1, key 2, which are keys, and value 1, value 2, which are values, where key value 1 is in M, the map in this case, and key 2, value 2 is in M. If key 1 and key 2 are the same, then value 1 and value 2 have to be the same. This is a bunch of mathematical jargon that boils down to you cannot have duplicate keys, but written in a way that's confusing. Okay, this formally states the function property for a set of ordered pairs where the keys have to be unique. Okay, so the domain, which we're going to be talking about domain and range here. When we talk about maps, when we talk about the keys, and then we talk about the values, the domain of a map is just all of the keys. The range of a map is just all of the values. So when we talk about the domain of a map, we're talking about the set of unique keys. When we talk about the range of a map, we are talking about the mathematical string of all values, which again can contain duplicates. So how is the domain modeled? It's modeled by a partial function, which is a finite set of K or keys, which satisfies the condition that for all key K, if key is in the domain of M, so if key is in M, the map, if and only if there exists a value V, then the key value pair is in M. So a key must have a value, essentially is what they're saying. There has to exist a value V for a key K in order for there to be a pair in the map. This is linking the key and the value mathematically so that you cannot have just keys that don't do anything, that don't point anywhere. And you'll see when we get into the range of them, you'll see that the opposite holds true, that a value that exists in the range of a map has to have a key in the domain of the map, which is here. The range of a map is a partial function. It's a finite set of v, which satisfies that for all value v, if there is a value in the range of the map, so if there is a value in the map, then there must exist a key. And if that condition holds, then the key value pair is unlimited. Mathematical jargon, again, if you want to dive into the weeds of this, you can, although I don't think you would ever get asked a detailed question on mathematical notation of the mathematical model of a map. It would be a cruel and unusual punishment to do so. And then tidying all of that up, we have that type map is modeled by a partial function. If you take one thing away, it's modeled by the fact that keys are unique, values are not, and there must exist a mapping between a key and a value if you have a value or if you have a key. Okay. Any questions on the mathematical model of maps? Lovely. Okay. The no argument constructor, we never have any argument constructors for these data structures that we're talking about. Ensures that this is an empty set of pairs because we'll get into it, but maps store this nested data structure called a pair in Java. So defining a map data structure is very similar to the way that we define other Java OSU CSE components, in the fact that we begin on the left side, as always, with the name of the interface, which in this case is map. The difference being that now we have to provide two reference types as to what we want to store. We have on the left side what we want the key to be, so in this case string, and then on the right side we have what the value should be, in this case an integer. So essentially what this is saying is I want to make a map that maps strings to integers. I want to call it M, and I want to use the implementation map1L. And then you could include string and integer within these less than or greater than brackets, but you do not need to, because Java can infer it based on this line of code here. And afterwards, our state contains now an empty map. What that picture. Okay, now let's jump into the methods. The first one is add. It takes in a key k and a value v, which adds the pair key value to this. That is an alias. It updates this. Requires the key is not in the domain of this because you cannot have duplicate keys, and ensures that this is equal to the old value of this unioned with the pair key and value. So the pictures today are going to get this. We have a map M. Map M points to a data structure. I draw largely because it's here, where that first entry, we'll just call this pair 1, maps to a pairing between a string PB and the value, which is and we have a second value here, third one, actually, which has a pairing between BW and 17. And then finally, we have a key, which is just a reference location string that points towards PS. And then we have V, which is an integer, which points towards the value of. So you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9 references in just this singular example where it only looks like we're defining 3 things. But you have the map, which is a reference location. Contained within that map are 2 references to pairs, and contained within those pairs are 2 references to reference locations. And then you have your string and your value. So it's very much complicated, or more complicated than, say, a queue where you're just storing reference locations. Here you're storing a reference location to a reference location to an object value. So when we call add, what the map class does for us is it packages this key and this value into a nice little pair. And it stores that pair in the map. So afterwards, you'll see that we've added this pair to the map. Oh, is the requires clause satisfied? Okay, actually, quick knowledge check here. What is the domain of the map before we call the add method? Yeah. Yes. All the keys, we have P, B, and W. So back to the question at hand. Is the requires clause satisfied? Remember that the requires clause is that the key is not in the domain of this. Is it satisfied? Yes, because PS is not PB or BW. So that's the check that Java goes through every single time that you call the add method. Afterwards, we have the map, which now contains 3 pairs, which all point towards their own reference locations, K and V. And then we still have K and V, which are aliased. So be careful, because if, say, your reference types are mutable types and you change them, they will change them within the map if there is an alias, and that is no bueno, not good. Okay, here's where we get into the pair interface. So the map interface includes an interface, a nested interface for another generic type, map.pair. Its mathematical model is simply an ordered pair of a key and a value. So formally, the type map.pair is modeled by a key and a value. No constraints on this, because the constraint is enforced in the map interface, where keys have to be unique. Fortunately, the map.pair methods are few. There are only 2. They have what are known as getter methods. .key returns the key, or the first component of this, and .value returns the second component of this. So these right here are technically a separate Java data structure. They are map.pair classes. And map.pair classes have 2 fields. They have a key and a value, which are both reference types, as you can see there. Okay, questions so far on maps and map.pairs? This gets into like one of the beauties, I don't know if it's beautiful per se, of object-oriented programming, which is that you can have classes nested within classes. So you can have a map class, and in that class, you can have a nested pair class. So each map has sort of a list of pairs, or a collection of pairs. Okay, remove, as you might have guessed, removes this, the pair whose first component is key and returns it, updates this, requires that the key is in the domain, ensures remove.key equals key, and remove is in the old value of this, and this is equal to the old value of this without the removed key value pair. Something to note is that you only pass in the key. So the only thing that you need to remove a pair from a map is the key. That's usually how it's done. Maps are used pretty often, I would say, and almost always they are removed by the key, because keys are unique. So if you know the key, you know exactly what value you're trying to remove. It would be way more difficult to say, try to remove something by the value, because there can be multiple values linked to multiple keys. You'll notice that this returns a map.pair. So when you are removing something from a map, what you are getting back is not, say, both the string and the integer. What you're getting back is this component here, this map.pair. So if you wanted to get, say, the key or the value from the map.pair, you would have to extract it from the map.pair data structure that's stored within the map. You can't just treat it as if it's its own thing. So we have PB99, BW17, and we've axed this third key value pair because we don't like it. And we're saying that the map.pair of a string and an integer called P, which we are defining, where's my chalk? There, should be equal to the result of removing the map.pair mapping between a string and an integer from map M with the key of K. So in this case, K is a string. BW. We're saying go through the map, return to me, and remove the map.pair that is stored with key PBW. So what happens is this gets axed, and now we have an alias to the map.pair. We're storing a variable called key. And then BW stays the same because we're just using it as a means to an end to return the key value pair. Now, again, going back to the idea that this is a pair and this is not just a string or an integer. If you wanted to say get the value of BW, what you would have to do is you would have to call b.key, or you would have to call p.value in order to get an integer, which is associated with it. And what this does is it unboxes the pair and gives you the actual key or the value. Let's say instead of defining an integer p, you just called out.println m.remove k.key. What that would do is it would print out the key. That value will return the value. So kind of like how you were able to, with XML trees, call .child0, .child1, .child2, .label, .equals Stephen. You're able to nest these statements and it'll return something which you can then call methods on, which you can then call methods on, and so on and so forth. Okay, remove, good. Awesome. Okay, remove any. Same thing, returns a map.pair, a key and value, and it returns an arbitrary pair from this. Updates this, requires that there's actually elements in it, and it can return any of the pairs within this. So this is a way, if you remember the set didn't have a defined order. The same is true of maps. Maps do not have a defined order to them. And so if you wanted to say, loop through all of the key value pairs in a map and modify them, you would have to use the remove any method and slowly go through all of the key value pairings. Now, if you wanted to go through all of the key value pairings of a map and modify them, why could you not just use a for each loop? Why do we have to use the remove any? Yeah.
You can't like affect the value of what you're like iterating.
Exactly. One of the stipulations of an iterable is that you do not modify the values of the things that you're iterating over. So if, say, this was people's scores on a midterm and their initials, and I wanted to apply a 1-point curve, I could not use a for each loop to just increase the dot value of each method or of each key value pair. I would have to use remove any, grab the value, increase it, restore it, add it back to the map. Okay. Remove any returns anything. So this could return PB, BW, PS. It could return anything. In this case, the example, they return PS, which is an alias to the map.pair string PS linked to the value 99. And again, that's a pair, so keep that in mind. It's not a string, any value. Okay. Value reports the value associated with the key. Does not return anything, but it simply tells you, based on the key value pairs that we have stored within the map, what is the value associated with the key that I'm passing in to this dot value function. So for instance, if you wanted to check what the value of a pairing in your key value pair was, you could use this. So we have PB 99, 17, and then we have PB and negative 4.3. Value is negative 4.3. Okay. So after we call this method, we are going to get that P, A is still equal to PB, but V is an alias, I believe, or it's a good question. Let me go back to the contract. I don't believe it alias, it does. Okay, so it's an alias to the reference value pointed towards by EQ PB. So long arrow here, but now you have a reference to the value 99, which if it's a mutable type, you could modify, and you could modify it within the map, which is dangerous. Okay, note the alias you created here. You should be able to draw the appropriate diagram showing it, which we just did there. Okay, HasKey reports whether there is a pair in this whose first component is a key. So this is something that you should probably call before you try to get the value of a pairing in the map. If you don't know if it has a pairing, with the key value equal to K. So if we have a map PB, BW, and then we have a string PB, and we call map or Boolean B equals M dot has key K, where K is PB, is this going to return true or false? True, because it is in the set of, or in the domain of keys. So that will return true. And if it wasn't contained within the map, it would return false. Size, everybody's favorite. I'm excited. I'm going to ask it. If we have, it doesn't even exist there. Okay, if we have a map of size 2, where there's 2 map dot pairs in it, and we call size, what will it return? 2. Okay, good. One of these days, size is going to return something completely different. Probably not. It's actually not. It's the last one. Okay, replace value. This one is where things get hairy, as always. Replaces the value associated with the key that you pass in. This by the value and returns the old value. So it's a way to swap out or replace a value in a key value pair in a map. Lots of nested things going on. It has an alias, which is the reference value this, and updates this. Okay, let's draw the picture. So we have PB, BW. Those things don't need to say. We're pretty much golden. So, okay. And so what we're saying is that old V should be the value of replacing the value that is linked to by key K with V in map M and returning the integer. So what we do is we go to the key value pair stored here and we replace the value with an alias to V. And then we're saying that old V should be a reference type. Wake up. Thank you. To the old value. There. Okay, I think that's right. So we have PB, which now stores 85. Oh, did it? Wait. PB. Oh, did I replace the wrong one? I replaced the wrong one. This should be, this one should point towards 85. Jeez. I'll probably get the eraser. This one should point towards 85. This one should stay pointing towards 17. And then old V should point towards, well, I deleted it, the old V should point towards 99. Okay. All right. I gotta wash my hands. So we have PB, which stores now the value of 85. We have BW, which stores not 17. We have K, which is still pointing towards PB. We have V, which is pointing towards 85. And then we have old V, which is pointing towards 99. Lots of values. Please draw pictures, especially if you're working with maps, because there's just too many references. Okay, now note the alias that you created here. PB is pointing, or the value in the pair linked to by the key PB is pointing towards 85, as well as that integer B, which you have, also points towards 85. So that's aliased. Okay, now we have another example. This one is the swap one. Let's see if we can do it correct this time. I'm going to use the eraser instead of messing up my hand, which will in turn mess up my jeans, and then people will look at me like, why do you have pink shuffle? BW 17. And then we have K, PB, and then we have V 85. Okay. So we're replacing the value. So V should now point towards 99. And the reference location pointed here should take a long way around for the point towards 85. And we replace the references. So this is a way to replace the values within a map if you want to. Where the key is still pointing towards, what is that, 99? Yeah, wait. K, oh, is pointing towards PB. V is pointing towards 99, which was the old value linked to by PB. And the new value in the map is pointing towards 85, which is all the way up there. Okay. Replace value. Good. Similar to all of the other times that we've done replace value, but this time with more references. Swaps V with value in M that was previously associated with K. Okay. KV reports some key associated with value in this. It is an alias reference to returned, or it aliases a reference returned by key. Notice how it says some key associated with the value in this. This is because values are not unique. And so this could return any of the keys that are linked to by the value that you're passing in. So we have back again. We have PB, which points towards 99. I left my chalk over there. PB points towards the value of 99. And then we have K, which points towards now XYZ, switching things up. And we have value, which points towards. And we're saying return to us the value return to us in key the key that is associated with value V, that is associated with value 99, which is BW. And so we alias this K to not point towards XYZ, but to instead point towards the string PB, because that is the value or the key that is associated with the value of XYZ. Okay, so the method value that we talked about before, where you give it a key and it gives you a value, is part of the intended use of the map and is efficient in most classes that implement map. This method key is rarely of interest and is inefficient in most classes that implement map. Because the fact that you can have multiple keys linked to the same value, this is not usually the way that you want to go about looking for things, diving into a map, because otherwise you will have errors. You can do it, the option is there, but just because the option is there doesn't mean you should do it. A good life lesson. Just because you can doesn't mean you should. And then it has an associated has value where you give it a value and it reports whether there is a pair in this whose second component is a value. This will work for any of the pairs that have that value. So if we have PB 99, BW linked to 17, and then we have our value, which is 17, will Boolean B M dot has value return true or false? Oh, wait. We got true. I heard it. It'll return true because one of the values is 17. Okay, cool. Has key is the other one is in part of the intended use of a map and is efficient in most classes. Has value is rarely of interest and is inefficient in most classes that implement map. Just because you have the option to look for something by the value does not mean you should, and you probably should not. Actually, you definitely should not. I don't even know why it's there, to be honest. They should probably cut it in the next update of OSU CSE components. Or write a patch note. Okay.
This is an OSU CSE component.
This is, yes. However, I will say most of these have Java equivalents. So things or what am I trying to say? Data structures in Java that are pretty much exactly the same as OSU CSE components, although slightly different. OSU CSE components, as you may have guessed, are not the industry standard across the world. So if you're in like a job interview, don't be like, oh yes, I know what a simple writer or a simple reader is. Unless they went to OSU, they will not understand that. You spend like 2 weeks at the end of software 2 saying, okay, by the way, all these OSU CSE components are not actually real components. They're just fake ones we made up.
Does anyone else use Simple Writer?
Nope.
It's just us?
It's just OSU.
Just for fun?
Yeah, for fun. Yeah, because we hate you guys. No, it's actually, I have no idea why we don't just use scanner. There is okay, so we have time. I'll talk about it. The reason that we use custom components is because all of these, I'm going back into the diagram. In software 2, you get into the fact that you have to write your own implementations of, say, stack, queue, set, sequence. And then the way that you can implement them is very different depending on what you want to do. So for example, you could implement an array or a sequence as a set of two stacks that are flipped on their side. And you just add elements from one and remove them from the other, which is like a weird thing that you do in software 2. But it teaches you that implementations of these classes can be done in many different ways. And that's the reason that we have custom components, because you can't really do that with regular Java components. So there's a bit of a hint for software
Do we
2.
use more custom components in other languages like Python or
Like OSU CSE components, or
Yeah.
no?
it's just Java?
Yeah, it's actually just Java. You'll get into systems 1 and 2 where you just learn C and assembly. You just use like vanilla C and assembly. And then foundations, you might not actually write any code. There are some classes of foundations 1 and 2 that have you write code. I didn't have one. Foundations 1 and 2 are basically just a math class that's cosplaying as a CSE class.
Was that the one that you said was hard, or was it like?
It's hard, but it's interesting. Yeah.
Okay.
Foundations 1 and 2. You'll probably have to take it. Well, you will have to take it. It's fun. It's fun. I swear. I swear.
Okay.
Okay, where were we? After we had our mid-credit scene for software 2. Okay. 53. Oh, did I skip 2? Oh, I did. Okay. Thank you. Combines M with this, updates this, clears M. So it's a way to combine two maps. The only stipulation being that, of course, because keys have to be unique, the domain of this and the domain of M, the domain of this intersecting, there's that string theory that comes back, with the domain of M must be empty. So there must be no keys in this which are also in M, and vice versa. So if we have PB 99, BW 17, and PS 99, you call M dot combine with M2. M1 will have all of the elements, M2 will have none of the elements. It's a way to combine two maps if you have two maps. So let's say that we were merging all of the software 1 classes, where the integer was your bug ID number, and then the value was the string with your name. We would be able to do that. We would just combine all the classes using a bunch of combine with methods. We could actually chain them together. We could do like Steven's 8 a.m. class dot combine with Bucci's 8 a.m. class dot combine with Steven's 9 a.m. class dot combine with. It would be a beautiful line of code. Okay, shares key with is probably what you should call before you call combine keys with. Reports whether this and M have any keys in common. So it basically just looks at the domain of the keys and the values and reports whether or not they have any similar keys. So M1.shares key with M2, where all of the keys are distinct, is going to return false. It doesn't have another example, but say this was PB instead of PS, then it would return true. And you could know that you could not, in good conscience, combine the two maps together. Okay, now we get into the iterator. Because the iterator combines or iterates over the map, this will return to you all of the map.pairs contained within the map. It has that same contract, which ensures that the unseen elements and the seen elements combine together, give you the whole thing, and then the cardinality of this dot seen and this dot unseen is equal to the cardinality of this. So we're going to go through this based on an exemplar. Suppose that you have a map that keeps track of all of names and associated salaries of the employees within the company. So you have a string which links to a natural number as opposed to an integer, and you have that implemented as a map 1L. So sample for each loop. Danger. Here's how you might try to give every employee a $10,000 raise. You have your raise number, which is a new natural number 2, which is a value of 10,000. And then you're saying for each map.pair, string, and natural number P. So you're saying for every pairing that exists, which is a string to a natural number in the map M, I want you to get their salary by storing it in the P.value and then adding to that salary the raise amount, which is $10,000. However, draw this diagram. P holds the alias to some key and its associated value in M. The method value returns an alias to that, both even though no map method is called within the loop. So you might be thinking that because you're extracting the value first, that this is okay. But here's how it actually goes down. We will draw the diagram. Important. essentially this will end up boiling down to, you're not allowed to change the values. But we have M, which we're going to say is the most boring map of all time. It contains a single key value pair, where the key is, what do we say, string. Oh, well, no, this should be a key value pair, so go return. String of references, where the string is saying my friend Teddy. And his salary is $20. That's right. And then we have salary or raise, which is 20 for $10,000. Right, and we're saying for each map dot pair P in M. So what this is going to do is it's first going to set P each time through the loop, pointed towards the map dot pair. And then we're going to say salary should be equal to P dot value. So we have salary now. It's this. And now we're calling salary dot add raise. So this afterwards, Teddy is getting the greatest raise of all time, and you will now be making $10,020. You might be thinking, hey, because we extracted the salary first from the map and then added it to the salary, we're not technically violating the constraint that you cannot modify things in a for each loop. However, because it's an alias, as you can see, you have modified the pairing between the key and the value. So that's where aliasing comes in. This is dangerous. And this whole paragraph says, incidentally changes the values of both P and M, where M is the mapping, because there's aliasing. Which you cannot do. It's illegal. This violates the rules for using iterators and for each loops. So here's how you should do it. You should have a raise, which is a new natural number, value 10,000. You should have a temporary map, which you then transfer from the actual map, and then you use remove any, you add the value of the raise, and then you add that key value pairing to the new map. So I'm not going to build the entire diagram, but what you essentially do is you store everything in a temp map, say, and then once you go through the same process where you extract out the parent in P, actually it's like the same thing, and then you call P.value.add raise, which adds that. Now what you can do is, because you have a new map, what you're essentially doing is you're adding a different pair, a different key value parent to the new map, which is new values of 10,000. Fine, and this was removed, and we call it removed. So it's just the parent. Right. You got value done. Right. And then the next time that you remove a pairing from the list, let's say here we had another pairing, just for demonstration purposes, which was Stephen. And Stephen's salary is actually $1 million trillion. Now, when we call remove any, so refer the pointer to here, and then it'll add the raise, and then it'll add it back. That is actually my salary from OC, by the way. They pay me very handsome, $10 million. Okay, I think that's it. Okay, draw this diagram. We did. It's not dangerous because there's no dangerous aliasing. We're not modifying the values within the map. We're modifying the values within the temp. Or we're removing them. We're removing them from the temp map first, modifying them, and then adding them to a new map, which is the way to do it. Okay, I can see resources. If you hate the way that I taught this, you can look at the documentation yourself. It's way fun. Okay, questions on maps? Going once, going twice. All right, sold to the extra 9 minutes that you have with your day now. Has it started raining yet? It's supposed to like pour all day.
It was really bad overnight. I don't know if you heard it.
Yeah.
I have dogs, and I have one dog that's really, really nervous with storms and stuff.
Oh.
And I had to let her out of the cage and let her sit in my bed.
Yeah. Yeah, I'll pull up attendance. Oh, by the way, if you came in late, I swear I'm not doing this on purpose, but lab also has to be asynchronous tomorrow because I have to go to a conference in Kentucky. So do not show up. I'll send out a reminder in Slack as well. But yeah, I like play rain noises at night, and I like didn't even have to do it last night because I could just hear the rain noises. I was like getting ready to put them on, and I was like, hold on, wait.
Analog natural rain.
Yeah, exactly. As opposed to the digital fake rain.
Did you see the hail yesterday?
No, when did it hail?
Some point in, I want to say like 2 o'clock. My wife texted me about it again. My dogs let me know because they're like downstairs crying. So like it's like just coming down on the house. And it was like she showed me a video of it, and you can't take video of rain, but like
Yeah.
you could like
You
see
see the
it
hail.
actually looked in the video like it was actual rain, which meant it was like,
Like,
they're like gumball
yeah.
sized.
I remember it. I
Oh,
remember.
I slacked you at like 11:30, so.
I know. I was
I was not
I was
expecting you to
asleep.
see.
Yeah, I go to bed like 9. I'm like 80 years old.
And then, I accidentally turned in homework 18 late,
Okay.
but I have proof that I did it for the due date.
Yeah.
So could I show you that so I can get it
Um,
graded?
I don't know why you would lie about something like that, so I can just.
Are you sure?
Because like, what if you're lying and you don't actually have the proof? And I'm like, okay, yeah, show me, and then you're just like fucked. Okay, wait, stop
Um,
sharing my screen. Oh wait, I gotta end the.
Is it